Greetings and welcome back. In this video we'll be doing a very brief introduction to alkenes as a functional group and then getting into how we name alkenes. So very briefly, remember that alkenes are carbon-carbon double bonds, and as such the hybridization of each of those carbons is sp2. sp2 carbons have a leftover p orbital, so really when they stack side by side, each of those carbons has an unhybridized p. They have a sigma bond in between, and then those two side-by-side p orbitals overlap to make a pi bond. They will then each have two more bonds. From the point of view of kind of looking at this thing on the side so that we can see that pi bond up and down, you've got one group on each carbon coming out at you and one going away. So these are planar. They're completely flat, and they can't rotate at all. The p orbitals need to stay side by side, so they're stuck in space, and those four substituents, 1, 2, 3, and 4, will always remain in the exact same position relative to each other. A pi bond is inherently more reactive than a sigma bond. If you look at the location of the electrons in a pi bond, they're held much more loosely, and they're kind of sticking out into space. They're quite polarizable, which again means that they're relatively squishy. And they tend to pull electrons away from other carbons. So think of a pi bond as more or less being an electron sponge from other carbons. So you tend to have polarity going in the direction of the pi bond from the other bonds within the molecule. As a result of this, that pi bond is relatively electron-rich, and it's also loosely held in space. So we'll get to the reactions in the next chapter, but largely they're based on the fact that pi bonds have these electrons that are loosely held, floating in space, and they're actually relatively electron-rich because they're pulling electrons away from their neighbors. Pi bonds are also shorter than just sigma bonds. So whenever we have a double bond, it's going to be shorter than a single bond. It's got more electrons holding it together, and so those nuclei are kind of squeezed a little bit more tightly together. And lastly, what happens with pi bonds, and alkenes in general, remember, is that to make an alkene, you need to remove hydrogens. So to get to the one that we have drawn above, really the biggest difference is that you would need to kick off two hydrogens in order to get from an alkane to an alkene, and therefore they don't have as many hydrogens as possible. Therefore we would say that they are unsaturated with hydrogens. So an alkane is saturated with H's, and we say that an alkene is unsaturated. Alright, so that's a very brief intro, and we will move on right now to talk about the naming. When we name an alkane, essentially we do the same thing that you do when you convert the word alkane into alkene. Alkane ends with ane, alkene ends with ene. And therefore, we take anything that's, say, propane and turn it into propene. So we drop the ane and replace it with ene. So for instance, here's a 4-carbon chain, the double bond on carbon number 1. 4-carbon chain is butane, so this would be butene, because it's now a 4-carbon alkene. We also have to use a number to indicate where that double bond is, and just like substituents, we want to try to minimize that number the best we can. So when we look at numbering, we could start at the left or the right. When we number the location of an alkene, we use the number where the double bond starts. So we don't have to go through and tell us that it goes from 1 to 2 because it is part of the main chain. Therefore we just say that it starts at carbon number 1. If we had the kind of numbering in blue, we would say that it starts at number 3 But of course we want to minimize the numbers, so this molecule would actually be 1-butene, and we would use the numbering that you see in pink. All right, and that is the really basic introduction to naming of alkenes. There's a little bit more to it, but this is the main thing. You take out the ANE, replace it with ENE, and use a number to indicate where that thing is. If you have multiple double bonds, so let's say with this thing right here, we replace that ANE with a diene. Diene, of course, would be 2 alkenes, which we see in this case. The reason that we leave an A in there is because we like to have vowels come after consonants, and if you take alkane and just replace ane with diene, then you would have alkdiene. And we like to say alkadiene because it just flows off the tongue so much more easily. So in this case, we would start numbering from the right side, because that's where the first double bond would be. And we would use both of those numbers. And so we have one double bond that starts at number 1, and one double bond that starts at number 4. So we would name this guy as hex, which is like hexane, and we would say hexadiene. And the numbers for this would be 1 and 4. Dienes and alkenes in general, there's 2 ways that you can put the number in there. The first is that you could just put it way out front, which seems nice and is nicest because that way the number is separate from the name. However, there's another way to do this, which is where you tell the reader exactly what you're talking about with the number. That is to say, we can say but1ene, which puts the number closer to the name of the functional group. Therefore, if you have multiple functional groups, it's really helpful because we have that number right next to the functional group that it is defining. So in this case, but for carbons, you stick the 1 in the middle of the word because the 1 expressly is indicating the location of the alkene. Likewise, with hexadiene, you could also call it hexa-1,4-diene, indicating that the 2 alkenes are at carbons number 1 and carbon number 4. The alkene is our first real functional group that we're naming, and what's very important with the alkene is we have a small twist on our rules for naming. That is that the longest chain needs to include the highest priority functional group. And since this is the only functional group with any priority up to this point, your main chain in an alkene must include the alkene, or that C double bond C. So I'll give you an example for this. If you've got a 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon chain, you've got a little 2 carbon fragment down here with the double bond, then the longest continuous carbon chain here would be 1, 2, 3, 4, 5, 6, 7, 8, 9. But since your main chain, which we define the naming off of, has to include that alkene, then actually our longest chain would be 1, 2, 3, 4, 5, 6, 7. So the main chain here, which again must include that double bond, would look like this. And then the rest of it would be defined as a substituent. So the longest chain isn't really necessarily the longest chain in the molecules, or the molecule. The main chain must be the longest chain that contains the C double bond C. So in this case, the name would be, well, we have a substituent on carbon number 1, 2, 3. So this would be a 3-butyl 1 hept. Hept is 7. Heptene. Or, of course, you could say 3-butyl hept 1-ene if you wanted to. Both of those would be correct. So let's move on to some more examples. With a ring, remember with a ring you can start numbering anywhere you want to. But the highest priority has to go to the alkene, so we want to minimize the numbers on the alkene. So we would go 1, 2, 3 around that ring, because since this is the highest priority functional group, you want to minimize it, or minimize the number on the alkene, before you minimize anything else. So we don't worry about really the location of the methyl group first. We worry about the location of the alkene. You might ask yourself, but we could also go 1, 2, like that, and that would still put the alkene at carbon number 1. The difference, of course, would be that if you use the numbering in blue, then we would have 3-methyl cyclohexene. And if we used the the pink numbering, we would have 6-methyl cyclohexene. Of course, you want to minimize everything the best that you can. So we would use the blue because that would give us the lowest number on the alkene and the lowest number on the methyl group. All right. So the last part of naming of alkenes comes from the fact that alkenes cannot rotate. So this molecule and this molecule would be different molecules and could not rotate to become the same thing. You'll notice that the one on the left is a 4-carbon chain with the alkene starting at number 2. And the one on the right is a 4-carbon chain with the alkene starting at carbon number 2. So both of those guys are 2-butene. So there has to be a way that we can differentiate them because they are different molecules. And the way that they differ is not really in the way that things are put together, but actually the way that they are arranged in three-dimensional space. So these are actually stereoisomers. And the way that we label stereoisomers is not R and S when we're talking about double bonds. We differentiate them as E and Z. So the rules for how to do this are actually similar for the rules of how to discern R and S. Remember when we did R and S, we ranked the 4 substituents 1, 2, 3, and 4. We ranked them based on the atomic number of the directly attached substituent. You're welcome to go back to the stereochemistry nomenclature section if you forgot that. But with what we did with these guys, that is to say chiral carbons, is we ranked them like 1, 2, 3, and 4. And of course we put 4 in the back and rotated 1, 2, 3. But the ranking is what is important for you to remember because we use the same ranking system when we do alkenes. We look at those 4 substituents, but instead of numbering them 1, 2, 3, 4, we number the 2 substituents on one carbon and then the 2 substituents on the other carbon. We rank them according to atomic number the same way we did with chiral carbons. So let's say we rank these guys as 1, 2. We only rank each side, essentially, as 1 and 2. Then we would rank the other side as a 1 and a 2. If those two things, if the 2 number 1s are on the same side of the alkene, that is to say, if you draw an imaginary line right through the double bond, then they're both on the same side over here. So here they're both on the bottom. We call it Z for zusammen, which is the German word for same. A lot of the history of organic chemistry comes from German. If, on the other hand, you have a C double bond C and you look at each carbon, and you rank those two things as 1, 2 over here, and 1, 2 over there, then you draw your imaginary line. Here we would see that the number ones are on opposite sides of that imaginary pink line. So if you draw a line straight through the alkene, just like this, they're on opposite sides. When they're on opposite sides, we would label that double bond as E, which is for entgegen, which is the German word for opposite. It's funny because we're kind of used to everything being, all of these abbreviations coming from English names, because English rules our world as the dominant language, but it wasn't so back in the early 1900s. It was all ruled by German, so the naming for alkenes stuck with E and Z. Alright, so let's go up and actually do this for the two molecules that we've drawn above. I'll go ahead and put in my CH3s everywhere as to not confuse myself. Okay, so what we want to do is we want to take each of those sides. So we'll look at what is effectively the right side. We will rank a C versus an H. A C would be our number 1, the H would be our number 2. Then we're going to look at the other carbon, and our C would still be number 1, and our H would still be number 2. So again, we're just ranking those two substituents against each other for each of the carbons involved in the alkene. If we draw our little imaginary pink line straight through the alkene, you'll notice that the number 1 on the left carbon, the number 1 on the right carbon, are both on the same face of the double bond. Therefore, it is a Z isomer. So this would be Z2-butene. Just like R and S, we often put that in parentheses out at the front. On the other side, or in the other alkene, we've got an H, which would be our number 2, and a C that would be our number 1. Then we've got a C that would be number 1, and an H that would be number 2. I know that this could get much more complicated, but we're still doing it the exact same way that we did over here with our R and our S. So again, if you've forgotten that, you can go back and look at how we prioritize those. But when we draw this line, you'll notice that on the top, our number 1, or on the right side, our number 1's up top. On the left side, our number 1 is at the bottom. So these are on opposite sides of that imaginary line. So this would be the E isomer, the opposite or entgegen isomer. So this would be E2-butene versus Z2-butene. If we go back a slide, we can see that this molecule right here actually has some E and some Z's that we hadn't talked about yet, but that we should pull out. So let's just look at that guy and we'll get rid of everything else. Woo. Woo. Alright, that's pretty good. And I'm going to go ahead and draw my hydrogens in, at least along the double bonds. I know that my 1s, 2, 3, 4, 5, 6 are still there, but that's okay. Alright, so when we look at this, we can go ahead and do the double bond at carbon number 4, looking at the carbon on the left and the carbon on the right. And again, all these guys have is a carbon, which would be number 1, and H, which is number 2. Then on the left side, we've got the carbon as number 1, the H is number 2. If we draw our imaginary line through that double bond, you would see that the 1's are on opposite sides. So my double bond at carbon number 4 is actually going to be a 4E, because the 1's are on opposite sides, and entgegen is opposite. However, if we look at the double bond on the right, we can rank the carbon as number 1 again, so we'll leave that number 1 there, and the hydrogen is number 2. We can't rank this one, because both of the substituents are hydrogens. Therefore, this double bond actually doesn't have any, I guess we would say, stereochemistry. It can't be either E or Z, and so it's nothing. It's like an achiral carbon. You can't rank it as R or S because it just doesn't have any type of stereochemistry affiliated with it. So in this case, we would have an E for the alkene at carbon number 4, but we would not have anything for the alkene at carbon number 1. So the way that we would amend this name is that we would stick the E in after the 4. Oh, I see what I did there. And so we would have 1,4-E hexadiene. Likewise, if we had a letter for number 1, we would say like 1Z4E hexadiene. I'm going to give you one more challenging example, and I would like you to try this on your own and bring your answer into class, and it'll be the first thing we go through in class. And then I'm going to give you a couple problems to work on as well. So here is a slightly spicier problem. I'd like you to go through and name that and bring your name with you to class. And what we'll do first in class is to talk about what your names are and how they jive with each other and the correct answer. So thank you very much, and I will see you soon.